Conditional probability. So finding the probability of things, but there's some known condition. Here's our rule. So if we want to find the probability of event A, but we know event B has already happened, so we know that to be true. The notation is this: A and then a vertical bar B. So that means probability of A given that B has happened. We know B happens. Then it's the probability of A intersection B, so the probability of them both happening, divided by the probability of B. Now, the other way we can do it is just counting the numbers in the sample space, and so it would be, well, it's a very similar formula. The number of items in the intersection divided the number of items in set B. And what that means is, if probability of A given B is actually equal to probability of A, then we know A and B must be independent events, because it actually doesn't matter about B. We get the same answer. Another way of thinking about that is if the intersection, the probability of that intersection is just probability of A times probability of B, and that's what we looked at yesterday with independent events. Remember we said if they're independent, then we just multiply the probabilities together. If they weren't independent, that then comes back to that counting formula we had where we had to subtract the probability of the intersection because we double counted. So if we don't have to do that, if it's just probability of A times probability of B, then they must have been independent. There was no intersection. So use this as an example. Mixed language classes, French, Latin and Japanese. There's our 3 languages you would have done back in year 7. The number of students who study each language, and there's a Venn diagram showing the different combinations of what people did. What's the probability that a student who studies Japanese, so that's the known event, also studies French? So we're looking for probability of French given that they study Japanese. You notice I didn't even write the formula down. If I've got the diagram, what we're essentially saying now is, well, yeah, it's a lovely diagram, but as far as we're concerned, the universal set now is just the Japanese, because that's the only thing that's happened that we know. Well, in that universal set, there's only 10 objects, and we want the French. Well, in the French part of it, there's 3. So 3 out of 10 is our probability for that one. We've got 2 boxes. Both of them have got 4 stones in them. The only difference between the stones is their colour, although in box 1 they're all the same colour, they're all black. In box 2 we've got 2 black ones, 2 white ones. First we're going to choose a box at random, and then we'll choose a stone from that box. So what's the probability that the randomly drawn stone turns out to be black? Okay, that's the first part of this question. Well, there's 2 ways we could do it. I could have randomly picked box 1, so that would have a probability of a half. But they're all black, so it doesn't matter then. No matter what I pull out, I'm going to get a black stone. So it's times 1. I didn't write the times 1 down, but times 1. Or, so plus, I could have got box 2, probability of a half. But now, in that box, there's 2 out of 4, so times 2 out of 4. So overall, we get a probability of 3/4 that we got a black stone. The other way I could have done this was say, well, actually, it's kind of irrelevant, the box 1 and box 2. There's no difference. So if I sort of push the 2 boxes together and said, oh, let's just pick a stone. And in that case, I'd say, well, I've got 8 stones all up, and there's 6 black ones. So 6 out of 8 is 3/4. We get the same answer. So there's part A. Now, we don't know which box the stone has come from, but given that we do get a black one, what's the probability that it came from box 1? Probability that it came from box 1 given that the stone is black. That would equal the intersection. So the probability that it's black and came from box 1 divided by the overall probability of it being black. So black and box 1, well, that's the one where I said was a half times 1. Over probability of black we just worked out was 3/4. So we have a 2/3 chance that it was box 1 that we used. In a school we got 55% male, 45% female. Now the male students, 13% of them say Monday is their favourite day because it's the start of the week and we love going to school on a Monday. While 18%, who are even keener, say Monday is their favourite. Find the probability that a student chosen at random is a male whose favourite day is Monday. I know that the probability of male is 0.55, it's 55% males. I know that the probability that they like Monday, given that they're male, is 0.13, because 13% said Monday is their favourite. So it was known that they were male, that was the known event, and we say, what's the probability that they like Monday? 0.13. I can use this formula, but rearrange it. So the probability that they like Monday, given that they're male, would be the probability of the intersection, which is what we're trying to find here if you look at it. What's the probability is a random male whose favourite day is Monday. So they're Monday and they're male. Divided by probability of male. So let's substitute in what we know. Monday male, 0.13. And then on the bottom of the fraction, probability of male 0.55. If I rearrange that, I can find out the probability that we're looking for, and it ends up being 0.0715. Here's one that occurred in last year's HSC, so the most recent one. We've got a bag, and there's 3 6-sided dice in the bag. Now 2 of them are regular dice that we're used to seeing, numbered 1 to 6. The other one is a special die, and its faces are labelled 1, 2, 3, but then the other 3 sides are all labelled with a 5. They're going to choose one out of the bag and then roll it. What's the probability you end up with a 5? Okay, probability 5. Well, what could happen? There's a chance that I pick out one of the regular sided dice, and there's a 2 and 3 chance of that, because there are 3, 2 of them were the regular ones. Now on that particular one, there's a 1 in 6 chance of rolling a 5. So 2/3 times 1 6. Or we could get the other one. There's a 1 in 3 chance of getting the other one. And on that particular one, there's a 3 in 6 or a half chance of rolling a 5. So overall, we have a 5 in 18 chance of getting a 5. Given that the die shows a 5, so there's the known condition. What's the probability that they selected the special one? So the one that had 3 5s on it. Probability that we got a special one knowing that we rolled a 5. Well, that would be the probability of the intersection, that both things happened, that's 5 and the special die, divided by the probability of rolling a 5, which we just worked out in part A. So special die and 5, well, that was the 1/3 times a half. Over the answer we just worked out, 5 on 18, we get a 3 in 5 chance. Another way I could do it, I could sort of use Venn diagrams, but I'm only interested in the 5. So I've got die 1, and as far as I'm concerned, there's just one number on die 1, and it's a 5. On die 2, same deal. There's one number on it, and there's a 5. On the special die, there's 3 5s on it. Everything else I don't care about, because I know we've got a 5. So if I now look at that, and it's saying, given that the die shows a 5, what's the probability that's the special die? Well, there's 5 numbers there. 3 of them are on the special die. So 3 and 5. Another way of approaching that question. That shall do us.